Hello, this is a video supplement to the article Origin of Iron 3 Plus in Iron-containing aluminum-free mantle silicate perovskite, published in Earth and Planetary Science Letters. The authors are Shenzhen, Sang-Heon Shim, and Dane. This video will be presented by Shenzhen. Our modeling work predicts that under lower mantle relevant conditions, the formation of Iron 3 Plus is not favorable in aluminum-free magnesium perovskite, and the Iron 3 Plus content profile has a concave shape with respect to pressures due to an Iron 3 Plus spin transition. Lower mantle has the largest volume fraction of the Earth's interior. The major components of the lower mantle are iron and aluminum-bearing magnesium silicate perovskite and ferropericlase. In this article, we focus on the aluminum-free iron-containing perovskite to help people understand the valence and spin state of iron under relevant lower mantle conditions. Here is a schematic picture of the structure of pure magnesium silicate perovskite. Magnesium atoms stay in dodecahedral site, surrounded by silicon-oxygen octahedrons. We will call the magnesium site A site and call the silicon site B site in the following presentation. If we replace a fraction of magnesium atoms by iron atoms in A site, then we will have ferrous perovskite, where the valence state of iron is 2+, and it's in high spin state throughout the lower mantle pressure range. Iron impurity in magnesium perovskite can also stay in 3+ valence state. The configuration of ferroperovskite is shown in the right picture. In this article, we only consider the charge coupled substitution for iron 3+ entering into magnesium perovskite lattice, which has already been shown to be stable in previous work. In this configuration, one iron 3+ atom stays in A site, another one stays in B site. The A site iron 3+ is in high spin state throughout the lower mantle pressure range, while for the B site iron 3+, it's in high spin state at low pressure condition, which is about 20 to 30 GPa. When the pressure goes up, the B site iron 3+ will gradually transfer to low spin state from 30 GPa to 60 GPa and then stay in low spin state down to the bottom of the lower mantle. This spin transition causes a volume collapse, which reduces the volume of the low spin ferric perovskite. Under lower mantle relevant conditions, iron 3+ can be produced from iron 2+ by charge disproportionation reaction. The reaction is shown by the following pictures. The reactants are ferrous perovskite and MgO in FCC structure. Under charge disproportionation reaction, the products are ferric perovskite with B site iron 3+ in a mixed spin state of high spin and low spin states, and metallic iron. Under lower mantle relevant high temperature condition, we build an ab initio based ideal solution thermodynamic model to find the equilibrium state of the system. It tells us the extent of the reaction and the ratio of iron 3+ content in the system. Here is the 2D contour plot of our calculated iron 3+ fraction as a function of pressure and temperature. We find that the iron 3+ fraction profile has a concave shape with a minimum around 40 GPa along any isothermal line. This is explained by the spin transition of B site iron 3+. At pressures lower than 40 GPa, the majority of B site iron 3+ is in high spin state with a relatively large volume. So when pressure goes up, it's enthalpically unfavorable to form iron 3+. When the pressure goes higher than 40 GPa, the spin transition occurs. High spin iron 3+ transfers to low spin state with a smaller volume. It makes low spin iron 3+ stable at high pressure range. Therefore, the iron 3+ fraction keeps increasing when the pressure is above 40 GPa. Here, we explicitly show the values of iron 3+ fraction along the geotherm pressure-temperature line. We can conclude that the upper part of the lower mantle contains a very small fraction of iron 3+, only about 0.01. Our results also indicate that effects of spin transition can result in complex depth variation of iron 3 plus fraction in magnesium perovskite, which is in contrast to some previous models where iron 3 plus fraction were assumed to be constant at different depths in the lower mantle. Our model predicts that iron 3 plus content in magnesium perovskite may reach a maximum near the bottom of the lower mantle, where the temperature and pressure are highest. It can possibly affect seismic properties such as density and bulk modulus, and also transport properties such as thermal and electrical conductivities in the lowermost mantle. Thank you for listening to this video supplement.